Greetings to all and welcome to the 10th International Workshop on Haptic and Audio Interaction Design, HAID for short. My name is Ilya Frussen and I'm one of the conference chairs this year, together with Vincent Levesque and Christian Frisson. I wanted to take a quick moment to introduce HAID to those joining us on the YouTube live stream who are not yet familiar with the HAID workshop. So the first HAID workshop was held in 2006. And its objective has been to foster interaction between a diverse group of communities that are interested in haptics, audio, and human-computer interaction in one way or another. And after that first meeting, 7 more followed, held around the world. After 2013, there was a hiatus of 6 years, but the workshop has made its comeback last year in Lille, France. And here we are in 2020 for the 10th installment of the workshop. Unfortunately, just like everyone else, we had to deal with the COVID-19 pandemic. This meant that we had to cancel our original plans for an in-person meeting in Montreal. And we had such nice plans, and I'll get back to that, what we originally had planned in a moment. So instead, we're doing this reduced virtual meeting, casting the workshop, at least for free and to the entire world. But back to the business at hand. This workshop has been made possible by the contribution of a great number of people, and I'd like to take a moment to acknowledge them here. So first, we want to thank the reviewers that volunteered their time to help us review all the submissions that we received. So I'll leave this up here for a moment so you can peruse it. Okay, so moving on. As I said, we had some nice plans. First of all, the meeting was supposed to be a 3-day event with 1 day dedicated to research and another day dedicated to foster interactions with local and international industry, a so-called Industry Day. And so while our plans didn't come to fruition, we do want to thank everyone that helped us to try and achieve those original plans before COVID-19 became a thing. So first, the meeting was set to be held at the ETS here in Montreal, who had offered the use of their wonderful facilities. We also had a great team on the programming committee. So first off, we had Juanita Marchand-Knight, who was in charge of diversity and inclusivity. Catherine Gostavino and Sylvie Ustad had agreed to be our program chairs. Francesco Tordini was helping us managing the sponsorships. And Pierre Majoric-Léger agreed to be our keynote speaker. The program also included a tour of the amazing facilities of the Center for Interdisciplinary Research in Music, Media, and Technology. And finally, there was going to be a live music event that was going to feature some interactive component as well. And Martin Marier was helping us, was putting that together for us. So we have a different lineup now. And we would like to thank also Vincent's students who are working behind the scene right now to help us keep things moving smoothly. Oops. So, hold on, something went wrong here. We also like to thank last year's organizers, Tomas and Marcelo, who are always ready to share their data, information, and knowledge with us from last year to make our decision-making that much easier. And I would also like to point out that last year's proceedings have now been published or are to appear in the September issue of the Journal of Multimodal User Interfaces. And as you can see here, there are 5 original contributions from that workshop that have been published in the Journal of Multimodal User Interfaces. And I encourage you all to check that out. Now, for today's business, the meeting has a very straightforward plan. There are 3 sessions, each with 3 talks. So the first session will be hosted by Vincent, and it starts off with a live talk followed by 2 pre-recorded talks. The next session will be hosted by myself, also starts off with a live talk followed by 2 pre-recorded talks. And the final session, no surprise here, again starts off with a live talk followed by 2 pre-recorded demonstrations. So just a final word about how we're structuring the talks. Presentations are 5 minutes and demonstration talks are 3 minutes, by the way, and each will be followed by a 5-minute Q&A. And everybody watching has the ability to participate in the Q&A. So we are using the Slido platform. So if you want to pose a question, please take a moment to go to this URL here, Slido, and you can use the event code 62272 to join. You can also find this information in the description below this live stream. So when you enter the session, you'll be taken to a very simple interface where you can enter your questions. And moderators will be selecting from among the questions and relay them to the session chair, who will be asking the questions to the presenter. So having said that, I would like to hand things over to Vincent, who is the chair of the first session. Thank you.
Thank you, Ilya. So my name is Vincent Lévesque from ETS in Montreal. I'm one of the co-chairs of the conference. I'm also happy to be the chair of the first session with 3 interesting papers on topics that are related to the 3 themes of the conference: audio, haptics, and interaction design. So we have 3 papers. The first one is about a very interesting effect of haptics on our impression of a speaker. The second one is about how haptic feedback can be used to help train a drummer with vibrations on the limbs. And the third paper is about a toolkit that can be used to facilitate the design of interfaces with printed actuators and sensors. So an interesting program, interesting papers, and as Ilya said, we'll be having presentations and then a Q&A session. I'll remind you that you can go on Slido and use code 62272. This information is online as well. Please send your questions during the talks, and we'll be monitoring them and then asking questions afterwards. So we'll start with the first paper. As I introduce the paper, I would invite Antoine to start sharing his screen to show the presentation. The first one is a live presentation. So the paper is titled Haptic Augmentation of Audio and Its Effect on Speech Perception by Antoine Verle, Pascal Fortin, Ferraz Taha, and Jeremy Cooperstock from McGill University. So with this, I'll invite Antoine to start his talk.
Thank you, Vincent. Hi, so I'm Antoine Verle from the Shared Reality Lab in McGill, and I'm going to introduce the work Haptic Augmentation of Audio and its Effect on Speech Perception that we did with Pascal Fortin, Ferraz Taha, and Jeremy Cooperstock. So first, let me introduce a bit of context for why we did this work, actually. In social interaction, being work, meeting, or just gathering, it's well known that we judge people based on a plenitude of factors, including a lot of nonverbal communication aspects. And it could be anything. Could be just the size of someone, the way he walks, charisma, really plenty of effects. But one that we found interesting is voice pitch. So it has been like demonstrated a bunch of times that lower pitch voices tends to get more attention in meeting. And we found that interesting because, well, for instance, in situation like the current pandemic, where everything is going to video conferences, and sometimes you don't even have a video, you just have the audio aspect, while you still have the fact that a lower pitch may get more attention. And that, as a result, created some unbalanced meeting because not everybody gets equal attention. And also, it's not really something that you can change. It's something that your voice is shaped a certain way. So the question we had was, is there a way to influence that factor by adding some vibrotactile layer on top of that? So the first thing we did was to create a setup for that. So we took a chair, an office chair, and we added 2 100-watt tactile transducer from Clark Synthesis Silver, and then we took all the TTS voices we could find for on Google WaveNet for English, and we created a framework to take the audio component and shape it into a haptic effect. It's like actually creating a new subwoofer, a voice, and the basic idea we had was the higher the pitch, the stronger the vibration. So every voice gets a vibration because we don't want to create a novelty effect. But yeah, it depends on your pitch. In this experiment, we reproduce a methodology from Klofstad et al. They did a study just based on pitch, and all the voices are saying, I urge you to vote for me this November. You presented a pair of voice with different pitches, usually. And then you have to choose which one was the most competent, the strongest, or the more trustworthy. In our case, we had the same voice with a low and a high pitch setting. We have a voice with and without haptic, and we have 3 male and 3 female voices. So a pair could be 2 of each of those categories. We conducted the study on 14 participants, 9 female, 5 male. And here is summing up the results. So each column presents a gender of the speaker, no, sorry, of the listener. So, and each line is the gender of the voice that you're hearing. And basically, based on our hypothesis, what we wanted to see was that the darker bar should have been taller every time. And as you can see, it's not strictly the case. And we have some interesting effects. For instance, male and female listener judges competence a different way. Like yeah, and that was puzzling for us. Also, yeah, you can see that for the main hypothesis would be strength, because we thought that vibrotactile would increase strength. It's not always the case. For instance, it works best on female listener. And yeah, a bit of like notes on that. The first one is, interestingly, if we looked only on the voice without haptic, we were not really able to replicate the previous finding, because on the Klofstad study, there was a clear effect that higher pitched voices were not chosen. It was all mainly the lower pitched voices. And here, we think that it's because we chose to use TTS voices, and we don't really know, because we took the baseline and we created higher pitch and lower pitch, but we don't know if the baseline is actually a good reproduction of what you could get on if you take a sample of recorded voices as the other studies. And maybe as well, the way we use robotic voices at different pitch sort of like created artifacts that diminish the way like listener likes the voices. But overall, it replicated our previous study on this setup, saying that it does have an effect on how we perceive the strength of the voice. It's not a huge surprise, because when you feel actually the whole chair is vibrating, it has some like really almost scary effect for some voices. And I'm happy to answer your question. Thank you for listening.
Thank you, Antoine. This is when we normally applaud. Sorry, it's a bit difficult online, but great talk. Thank you. Very interesting topic as well. We have actually one question already on Slido. For everyone else, again, if you want to ask your questions, please use Slido and event code 62272. The first question is about how you transform the signal from the voice into vibrations. And specifically, the question is, what method was used to drive the tactile subwoofers from the voice signals? Was it a low-pass version of the original voice signal?
So we tried a lot of different way. There's a low pass in the end. There's different layer. We use PIO, I think, on this one to do real time sound processing, and so we we sort of like invert the frequency. Like if there's a high frequency, it get shifted to a low frequency. So we sort of like invert the signal, and that way all the higher component gets pushed to the lower frequencies that would be played by the vibrotactile actuator. We also have apply a different gain based on the pitch. We've got some kind of equalizer for that, and in the end, we've got a low pass filter. And yeah, that's the processing.
Great, thank you. There's also another, not a question, but a comment that was posted on Slido. The person says, common finding, females are more sensitive to minor changes than men regarding changes in speech and adapt quicker than men over time. I don't know if this is something you were aware of. If you have any...
Yeah, like as I was saying, like there's we sort of discovered that there's really a lot of effects. It's really hard to that's why like initially we thought of using TTS voices, because we have more control on the voice. It may have been a bad design choice in the end, but we wanted to avoid every like quick changes, and even going male and female voices is something that we know that the effect do not replicate cross gender all the time. For instance, if we chose dominance because that's the one that seems to be the same. But if you think about seductive aspect of the voice, it would be actually for female voices, you may think that it was higher pitch voice that would get more selected. That's some trends that we saw, and it's really interesting research of the effect of voices.
Okay. We don't have any more questions on Slido, so maybe I'll ask one of my own questions. In the paper, you mentioned that there could be an impact on voice assistance of this kind of technology. I wonder if you could elaborate a bit more on what you were thinking of here as an application.
Yeah, so I mean, like voice assistant use TTS voices, and here I think that comment is related to the fact that what we find here with TTS voices does not replicate what you would find with real voices as well. So even if we took at the time it was the best TTS voices, Google WaveNet doesn't feel that much robotic. There's still, I guess, some cues that gives it up to listener, and we also think that well, when you're designing a TTS system, like it's maybe not the vibrotactile aspect, because I don't think I don't know if you would use vibrotactile feedback on top of your TTS. It's already a bit disturbing to have your Google Home or Alexa speaking to you. You don't have to have your whole house shaking as well. But yeah, like the pitch of the TTS is actually of importance in the way you listen to it.
Okay, great, thank you. So I think that's all the time we have for now, but thank you very much for your talk and for your answers. Very interesting work, thank you.
Thank you for organizing this.
Thank you. So now we'll move on to the second paper of this session, titled Haptic Tutor, Haptics-Based Music Education Tool for Beginners. And we actually have two of the authors with us today, Ajin Tom and Martin Daigle, who I believe are both in the session to answer your questions. This is a pre-recorded video, so I'll actually be sharing my screen right now. It'll take me a second to pick the right video. Here we go. So we'll play this video now, which is about 5 minutes long, and then we'll have a Q&A afterwards with the authors.
Welcome to our presentation for the HAID 2020 conference, presented by Ajin Tom and myself, Martin Daigle. The co-authors for this paper are Ankita Singh, Fabrice Marandola, and Marcelo Wanderley. Drum set is traditionally taught in the following ways. Visual is seeing another drummer perform and mimicking the movements that we see. Auditory is by hearing a drum performance and trying to replicate the sound that we hear. Logical would be reading sheet music and understanding the logic behind a drum beat. We realize that there's a strong haptic presence in drumming, but not as a learning stimuli. That's when we decided to use haptic to relay information about the drum beat directly to the student. We decided to film a pre-recorded drum lesson so that each student would take the same drum lesson. The vibrotactile bracelets relaying haptic information were secured on both wrists of the participant and on the right foot. We had 2 experiments, and Ajin will talk more about the conditions for the experiments in the next slides. For the first experiment, we presented the basic rudiments for the students, which are basic left and right hand coordination exercises. For the second experiment, on top of the rudiments, we added a linear beat which included the use of the bass drum pedal, which is triggered by the foot.
Hello, my name is Ajin. I will be presenting some of the technical aspects and results from our work. These vibrotactile actuators were developed at ITMIL lab. We modified the firmware to make it work such that it produces a vibration on the respective limb of the drummer. On the right, you can see the hardware configuration of a single vibropixel. The vibrations are produced by the combination of a coin type and cylindrical type ERM actuator. So this was the max patch that was used to make all our mappings. Basically, we could feed in the MIDI score of any drum beat that had to be produced on any DAW. The DAW would produce the MIDI messages which will be sent to the max patch, and the max patch would then transmit wirelessly to the vibropixels. As for the experiment setup, we have the drum teacher perform the drum lesson on a MIDI drum kit, and the drum kit then produces those MIDI notes, which are then mapped to the students' vibropixels for the actual experiment. So in this experiment, we had 13 non-drummers split into 3 groups for the 3 different conditions. 10 had access to the drum lesson. Basically, the subjects follow the video of the drum teacher performing as well as the instructions to the students. The next 10 had access to the same drum lesson as well as haptic pulse condition, in which the vibropixels triggered exactly when the drum stroke was supposed to be performed. And the third group, the last 10 subjects had access to the drum lesson again. But the haptic condition used this time was the ramp condition. In this, they had a pre-vibration after which the pulse occurred. So this basically gave an anticipation towards each drum stroke. As you can see in the table, for miss ratio almost got halved for the haptic conditions. So for just the drum lesson, we observed 35% of hits were missed, whereas for the haptic conditions for pulse and ramp, it was 15 and 17 respectively. Miss ratio also decreased over time for all the 3 conditions, but for the haptic condition, we observed a faster improvement in terms of miss ratio. We also measured asynchrony and IOI deviation, that is inter-onset interval. As expected, we can see low asynchrony and IOI deviation for the teacher. As for the students, we can see that for the pulse condition, the mean and standard deviation of both the metrics are much less compared to the drum lesson. The ramp condition performs slightly better than the pulse. For the second experiment, we had 16 new non-drummers, and each were split into 2 groups, 8 for the drum lesson and 8 for the haptics condition. In this, we were more interested in evaluating the effect of vibrotactile feedback when we moved from simple rudiment lesson to a more complex drum lesson that involved the foot. Just like in experiment 1, we can see lower asynchrony and IOI deviation for both the haptics condition. The ramp group coped better with increase in difficulty from the simple to the complex lesson. We also gave out a series of questions to gather thoughts from our participants after the experiment. These were some of the highlighted comments. Overall, we observed that the 3 objective metrics linked to accuracy and precision improved significantly when haptics was involved. We also learned that the kind of haptic stimuli had a significant effect on the improvement of these measures. Finally, we can conclude by saying that haptic stimuli does improve drum learning. Hope you enjoyed our work. Feel free to ask us any questions. Thank you.
So thank you for preparing this presentation. I'll invite now the 2 co-authors of this paper who are on the call, Ajin Tom and Martin Daigle to please turn on your camera and your microphone and join me for a question and answer session. So thank you very much for your work for presenting this here. So we don't have any questions yet on Slido. I'll remind you that you can ask your questions at 62272, the event code on Slido. To begin, I'll just start maybe with my own questions. In the paper, you mentioned something that I thought was interesting. You mentioned that this could be used to support children with disability to help them learn. So I was wondering if you could explain a bit more what you meant by that. What do you envision being, how do you envision this being used in applications for people with disabilities?
Yeah, exactly. So people who have difficulty seeing or have issues reading notes, notation that is presented to them, or watching a drum teacher perform and follow the actions. It's interesting that the other senses that they have access to is the sensation of touch. So in such cases, a haptics sensation makes a lot of sense in that they can actually feel the beats and try to perform those different drum strokes and eventually develop muscle memory and things like that. So we found that that's pretty interesting, an application to look into.
Okay, great, thank you. So we do actually have a few questions coming in. Well, let's see, I'll have to pick one. Someone is asking if you have any ideas why the REM condition produce faster learning.
Yeah, so the idea for pulse is that exactly when the drum stroke is supposed to be performed, they feel the vibration, right? But usually, if you look at a general way in which we learn drums, we follow a drum teacher in which we can actually see the anticipation towards the drum stroke, right? So to mimic a similar sort of anticipation, it only makes sense that we translate the same anticipation to haptics. So in the RAM condition, we had a pre-vibration that ramped up in terms of vibration energy towards that pulse, which had to be the drum stroke, right? So anticipation is the major factor that probably helped in faster learning.
Okay, thank you. A few more questions. One of them is, did you test the effect of beats, etc., that require multiple limbs to hit at the same time? So would it also work if multiple haptics are played at the same time?
Well, our technology and system does support multiple vibrations and multiple limbs. It's something that we didn't test because we didn't want too many variables changing at a time. So for now, we focused on one stroke per limb per vibration. And yes, for sure, it'll be an interesting future work that we aim to try out. Yeah.
Is that something you tried yourself just to see if it would kind of work?
Oh, yeah, sure.
Do you have any impression? No?
Yeah, so in pilot experiments, we did try things like that. Yeah, we have an hypothesis that it will be confusing to have simultaneous vibration on two limbs, but then we have to come up with good strategies that can help such situations.
Okay, interesting. So I think we might have time for one more question. So someone's asking if you had to do anything special to account for latency and jitter of communication with the vibropixels or the ARMs themselves. So basically about the timing, how good the timing has to be for this to work.
Exactly. So the vibropixel have an accelerometer embedded in the hardware. So basically, we kind of have a feedback loop in which any trigger for vibration that we send to the vibropixel, we also get a timestamp as to when the vibration actually happened, because the accelerometers inside the vibropixels give us that timestamp, right? And we know when it actually vibrated. So we conducted a few trials in which we tried to measure the end-to-end system delay, and we have a feedback loop in which we kind of pre-send the vibration control message. So this way we could account for end-to-end jitter and delay. For sure, it's not a perfect system. In real time, it's very tricky to rely on such a system, but we tried our best to make sure there is a minimal delay and jitter.
Okay, thank you very much. So we had one more question, but I think we have to move on to the next paper. So maybe we can have discussion offline about this one. But
sure.
Thank you very much for your time, and thank you for this interesting paper.
Thanks a lot for organizing this. Yeah.
Thank you. Okay, so our third paper is also a pre-recorded presentation, so I'll be the one playing the video. So the paper is called PrintJets, an open source toolbox for designing vibrotactile widgets with industrial grade printed actuators and sensors. So I'll just play the video right now, and then we'll have a question and answer session with Christian Fisson, the first author. Let's see. I'm sorry. Okay, there we go. Sorry about the delay. And there we go.
We present PrintJets, an open source toolbox for designing vibrotactile widgets with industrial-grade printed actuators and sensors. This is a collaboration between Christian Frisson, Julien de Codin, Mario Sanz Lopez, and Thomas Pietjak that started at INRIA and Université de Lille in France. This project was funded by European project Happiness for haptic printed patterned interfaces for sensitive surfaces. Physical buttons are common in our life across a variety of devices, but they tend to be bulky, hard to manufacture, and they wear out easily. Tactile solutions are already available, but they provide limited feedback, and they suffer some of the same problems. Our solution relies on printed sensors and actuators. They are made out of a conductive ink printed on a transparent and flexible substrate. Printed actuators and sensors come in various shapes and sizes to serve different purposes. We start by designing a layout for both actuators and sensors, first in 2D. To maximize vibration, actuators have to be clamped. We then model actuators and the clamping base in 3D. Actuators use piezo ink. Sensors use silver ink. By measuring capacitance, we use these as pseudo force sensors. Clamping bases can be prototyped by 3D printing with maker-grade equipment. The actuator is then glued upside down above the structure. Finally, we place the sensor under it. We use off-the-shelf boards to instrument capacitive sensors and drive piezo actuators, using an analog audio signal for prototyping or embedded waveforms for production devices. We use an open-source visual programming environment for data flows, pure data. Capacitance data can be processed from sensors. Actuators are able to produce vibrations, like loudspeakers. Our technology allows to replicate behavior of a physical button. By laying out multiple actuation zones, we are able to create a wide range of devices, like sliders or trackpads. We released libhappiness, our library for driving piezo actuators and sensing capacitive input, under the terms of the new Lesser General Public License on INRIA's GitLab.
So thank you, Christian, for sharing this video and for being with us today for a Q&A. Again, if you want to ask questions, I will invite you to go on Slido 62272. In the meantime, we have no questions yet. So in the meantime, I can ask maybe 1 or 2 questions myself. So Christian, in your paper, you mentioned that you haven't done any user tests yet with your system, but I was wondering if you could say a few words about your own experience. I'm assuming you used this yourself to design these 3 use cases at the end of the paper. So I'm wondering if you can say a few words about what your experience was like, if there's things that you think worked great or didn't work so well, if you have any comments on that.
Hi. So, Can you see me? Can people see me?
Yeah, we can see you and hear you.
Okay, great. So we were prototyping and designing interaction at the same time that these printed actuators and sensors were fabricated. So at the time, one constraint was that the vibrotactile feedback was quite weak. So it was very subtle, and many people wouldn't feel the vibrations. Even if you could see in the video that it could move like a small nail. So I believe it wasn't ready for user evaluation at the time.
Okay,
yeah.
but I'm assuming you use this yourself to design some effects. How well did it work? What is your expectation if you were to test this with users? Do you think they would appreciate it and be faster at designing with this?
Oh, so, well, I think that for using the software environment, pure data, one needs to have experience with data flow processing, audio synthesis. So it's more targeted to expert HAID authors. But it's the part of prototyping and design in the very beginning when we want to have a huge design space and be able to use all the huge background of sound synthesis that there is available in audio. For I don't think I would use this tool for teaching interaction design. I would stick more into the new tools developed by Lofelt or companies that to vibrotactile feedback.
Okay, thank you. So we have a few questions on Slido now. Some that you almost answered. Someone is asking more details about how strong the actuator is. And I actually had similar questions as well about what does it feel like when you use these different widgets that you created. So I don't know if you could tell me a bit more details about the sensations and the strength of the actuators.
Mm-hmm. So I don't have metrics in mind on like a displacement or the force, but it's quite weak. To give an appreciation, it's weaker than what one can get from a smartphone. So at the time, the way to increase the strength of the vibrotactile feedback was to stack more of these layers of conductive ink, but that comes with some challenges. So sometimes the fabrication fails and actuators become burnt. So we were quite early in the fabrication process.
Okay. And someone's asking what was the frequency range approximately of these vibrations. I don't know if you have any measurements on that.
So some of our partners measured that, but at least it could cover the few hundred hertz of the usual vibrotactile feedback range. That is like from a few to 400. I can double check that.
Okay, and I have one more question here from Slido as well about how durable. How do you compare in regards to durability versus larger physical models, the expected lifespan? So how reliable are these actuators, I suppose? Do they break easily? Will they last a long time? Do you have any idea about these things?
So, physical. I will use this as an example. Physical buttons, they tend to have mechanical wear. At some point, they might break. So here, the equivalent is one may pierce the membrane. It's kind of like a loudspeaker, and maybe over time there would be surface erosion. But we didn't conduct stress evaluation over time.
Okay, great. Well, very interesting work. Can we try this in Montreal, or is the prototype in France?
You would have to go to Lille, yes.
Go to France. Okay.
Or partners of the newer European projects that continued over. The name is Prestige, so including University of Glasgow.
Okay, thank you. Very interesting. All right, so I think that's all the time we have. So thank you, Christian. So that's the end for my session. We'll move on to session number 2, which will be chaired by Ilya. So I'll give you the microphone, Ilya.
All right, so we move on to the second session. So the first talk, we have again 3 talks, of course. The first talk presents a framework that enables us to move away from the current dull vibrations that most devices currently allow for. And the second talk dives into the world of virtual reality and how spatial sound simulation can help urban planners in making our cities sound better. Third paper also considers city sounds and presents a field study assessing the effects of an outdoor sound system on how people experience their environment. So I would like to invite our first speaker, Max Weber, to present his talk on Towards a Framework for Ubiquitous Audio Tactile Design. Vincent, if you could please switch there.
Yeah, here we go. Thank you for having me. My name is Max. This work is part of my thesis that I'm just concluding at the Audio Communication Group at the Technical University in Berlin. It's supervised by Chavez, who maybe some of you know in the research and from last year's publications. So the motivation behind this. First off, I want to facilitate that the tactile design could very heavily be inspired by the sound design process that we're already familiar with. So looking at audio tactile events in nature can inform us how to create realistic or simulate realistic interactions with tactile stimuli. And another thing that goes hand in hand with that is using audio tactile signal translation, which I think also in the previous talk was briefly mentioned when using the voice augmentation. Another issue that I want to address with this framework is the issue of hi-fi vibrotactile stimuli reproduction. So similarly, like in the 50s with loudspeakers, where there was no standard on what does high fidelity or HD haptics mean, we are in a similar position now and need to work against that or work together to clarify these terms. So there's a huge variability in actuator technologies out there in the market between different smartphones, game controllers, VR, and in research.
Excuse me, Max?
Yes?
We cannot see your slides.
Oh.
Can you please check if your screen share is on? Thank you.
I'm sorry, that is, thank you for bringing this up. Okay, so I already jumped past this. We're just on this page right now. So just again, the tactile design approaches. And this is where we jump in. So the variability in actuated technologies, the bodily interference due to varying modes of interaction, depending on how you interact with the device. And yeah, what I mentioned, the missing standards to evaluate and define reproduction quality to make sure what high fidelity or HD means. So we measured some smartphones just to give an idea, and a lot of you are probably familiar with this. There's a huge variety in the bandwidth that we have available in the hardware space, and you cannot go outside of this. You can probably boost some actuators beyond the limits, but this is not sustainable and they might break. And also they don't cover the entire frequency range of what we can feel, which is by literature up to 1,000 hertz or maybe 800 hertz, where it degrades steadily. So this showcases a need for a system that can adapt to these hardware capabilities and at least bring the best out of them. So this is part of the motivation for the framework. So the conceptual framework basically consists out of a few stakeholders, a few key stakeholders. And the idea here is that we capture the key requirements that arise from each perspective of these stakeholders. So the first one that I want to talk about is the designer, the one that creates the tactile assets. In this idea here, we use a similar to sound design, a curation process that uses signals, WAV files or something like that as the foundation or as a corpus from where we want to start creating. There's an analysis codec, an analysis part that then creates a versatile parametric tactile data model from that. And we want to facilitate authoring and editing tools that then can read this tactile data model and also save it again and allow comfortable editing of these stimuli. There's one that I didn't mention in the paper because it's not so important for the sender-receiver aspect of this, but the developer who needs to integrate these assets similar to how the developer would design the interactions for the sounds. integrate them into an application or an interaction. And next, we want to show the perspective of the hardware product owner who designs a hardware device and makes a choice on what type of actuator is needed or he wants to use in his application, he or she. The important part here is that we want to motivate that the measurements that I talked about in the standardization process could be part of an actuator-specific configuration file that then informs the resynthesis of the tactile data model. This would allow us to adapt to the capabilities of the actuator instead of sending a signal that is then poorly reproduced, or by creating poor signals for actuators that are actually capable of doing much better. In the end, obviously, we have the recipient, which could be the end user, who is completely blind to all of this and should basically just interact with the application and get a proper response that is reflects what the designer on the top half of this flowchart intended. So it's a lot about the intent of the designer and how this is reproduced at the end. We did a case study using the Core Haptics API because it pretty much encompasses almost all of these aspects. It has a native API consisting of intensity and sharpness steps that control the amplitude and frequency of the embedded so-called Taptic engine in the phone. And as there are different phone models and also different types of the Taptic engine, some sort of adaptive resynthesis is already happening. And in the paper, we benchmark or basically analyze the capabilities of the Core Haptics API on the iPhone 8 and compared to our expectations that are laid out from our idealized framework in the end. So the conclusions. Design process, we can use already existing design as sound design principles and natural events as a guideline to design tactile stimuli. We can counter the variability in actuator technologies by reproducing as good as limitations allow. We need standardization to measure and classify reproduction fidelity so that we have a common understanding of what maybe high fidelity or HD means. And we can facilitate an adaptive resynthesis where we can try to do our best within the limitations of the available hardware. So just quickly plug my thesis here. What we're talking about right now is chapters 1, 3, and 4 of the thesis, where I kind of lay this framework out. In chapter 3, I also talk about the bodily interference. This is going to be presented at EuroHaptics in September. So please come by in the Q&A session if you have time. And chapter 5, we also did a perceptual elevation of this entire framework of a prototypical version that I implemented. And this might be a forthcoming publication, unclear where yet. So thank you for your questions, and I'm happy. Thank you for your attention, and I'm open for questions now.
Thank you, Max. Very interesting. I hope this, this framework will move things forward for us all a little bit. So there are some questions on the Slido here. So one question, the context heavily influences the perception of haptics. How does that come into your framework?
Depending on what context means, I would say there's a variety that you can do. If this is a medical application, I guess it would be very heavily relying on what the purpose of that is. If it's a computer game or application, I think it's almost like an idiosyncratic way, or a way like similar to asking, is there an ideal sound for something? I couldn't answer that, I would say. I think similarly, there's not an ideal tactile response when it comes to the perception. I think this is all up to what the designer has in mind. If that answers the questions, otherwise, please follow up again.
Actually, there was a follow-up here, I just noticed. So the questioner follows up by, for example, signals that are clear when you are sitting still in a quiet room, maybe too weak to notice when you're running. So I think it's more the physical interaction with the haptic stimulus, how that context, if you like, affects how that is incorporated in your framework.
When you're sitting still in a quiet room, maybe too weak to notice when you're running. Oh, okay. I guess this is about the context at the playback time. I would say this depends heavily on the application and what the designer has in mind. Again, I would rely to say this is not something I would, that the framework is agnostic to, I would say. It doesn't really take this into account. It basically is a feed-forward system where the designer has an intent in the application with the developer, and then the reproduction is done pretty much feed-forward without any real-time feedback about the environment.
Okay, thank you. Okay, let me ask you one more question, and then I think in the interest of time, we need to move on. So how does your data model adapt to all these different kind of actuator technologies that are out there?
So
LRAs, ERMs, all these things.
Yes. So in the data model, I chose a parametric representation of the signals, which makes it very easy to map them frequency-wise and also amplitude-wise. And in the end, I think the most important thing is to get a good assessment of what the device or actuator is capable of, and to map the signal within the boundaries of that bandwidth and the dynamic range that is above the perceptual threshold. So anything that is available is used to its best potential, and anything else that can't be displayed is discarded.
Awesome. Okay, well, thank you very much. I think we need to move on to the next talk, which will be a pre-recorded talk. The title of which is, sorry?
I had to drop out on the sound, but I guess thank you for setting this event up. And
okay, thank you. You're welcome. So the second talk is an interactive soundscape simulator for professionals of the built environment. Vincent, if you could please start that video.
Hi, everyone. Thanks for coming. So today I'll be discussing a work in progress which involves creating an interactive soundscape simulator for professionals of the built environment. So here's a very practical roadmap to this session. I'll give an overview to the existing problem with urban noise management, and I'll introduce a long-term solution along with its barriers and how we're going to overcome these. So sound is considered quite late in city-making decisions. So due to this reactive model, we get a lot of noise pollution, which causes a lot of adverse health effects with expensive Band-Aid solutions. This also produces a mindset where we need to block out sound because it's all bad. That's not a great mindset to have. In response to this reactive system, we want to incorporate a soundscape approach to contribute to a long-term solution. This basically means that we want to start proactively planning for sound while using sound as a positive resource. We do this by considering the entire context of the urban space as it's experienced by people, and help cater designs to fit what people want it to do in that space. Now, when doing so, we can facilitate a lot of positive activities in a better sounding place and avoid many sound complaints in the first place. But these techniques are rarely used due to a lack of infrastructure for sound planning. Two reasons for this are that there is an insufficient curriculum and a lack of tools that allow professionals to do just that. As such, rather than designing nice sounding experiences, they're trapped in a system that values sound levels over positive designs. And not by choice, mind you. This is a systematic problem the world over. Sound is very tricky to deal with without any training or tools, or very minimal at least. So in response, we've been running professional outreach programs through workshops for several years now. We're currently in the middle of developing a new curriculum for sound planning, and we're developing an immersive soundscape simulator to act as a first tool. So regarding our workshops focus on knowledge transfer between academics and professionals. They seek to both train professionals and also to understand the needs of the professionals to help them do their jobs better. So we'd like to have this bi-directional relationship here. So only together can we advance this material to create some truly fantastic soundscapes. Regarding curriculum, the curriculum acts to retrain people's mindsets around sound and gives practical skills. So they provide these relevant skills to the right set of people. So there's a lot of knowledge out there, and not every professional needs every skill. So we want to be realistic about what people learn. With that said, everyone can benefit from understanding the wide-reaching philosophy behind soundscape design. Finally, a tool is in development to help non-sound related professionals plan soundscapes. So this is informed by both academic research and through working with and trying to better understand the needs of professionals. This helps take knowledge into practice, that valuable final step. So some major features of this include manipulation of sound sources in 3D space is an absolute must. We'll be introducing some new ways to visualize sound, different ways to design once, but experience in different contexts. So we can design during 3 p.m. in the afternoon, and perhaps let's do it at a different time of day to see the acoustic consequences of our actions. We'll be providing some built-in training modules, ways to import your own design models to ensure future usefulness beyond the training, and ensure that what you experience in the simulator will be a reasonable reproduction of what you can expect from your final implementation in the real world. Interested in more? Please read our paper, visit us on the web, or of course, give me an email. Thank you very much.
Thank you, Richard. Are you there? If you could please join us for some questions.
Yes, I am here.
Hello, Richard. The question came in on Slido about the spatial resolution of your system. So now I'm assuming the system hasn't been built yet, but maybe you can say something about what kind of spatial resolution you would want to have or you would need to have in order for this system to work properly.
Yeah, so that is actually one of the questions we'll be working on. So in terms of visuals, of course, the higher the better. It's ultimately going to come down to what is affordable by professionals. So those of us in big corporations or big research institutes, we're going to have access to a lot of fantastic hardware, but we want to make this able to be used by just about anybody. So right now, what we're looking at in terms of like we're developing using a Vive Pro right now for visuals. In terms of audio, we're currently looking at, or we're going to actually be exploring and testing different options through like simple stereo. We're probably going to try to avoid if possible. But it will be an option. We're trying to be doing an ambisonic system through playback for multiple people. So we have, we'll be looking at binaural recordings and processing. So we're still exploring the actual hardware we're going to use in the end, but we're looking and we'll be testing as much as we can.
So has there been any talk about maybe using some non-individualized HRTF kind of technology? Yeah,
so what we'll probably be doing is we'll probably be picking maybe about 4 or so different general ones, and we're looking into the options of just having people undergo like a quick kind of training session to see which one would be best for them. But right now, like we definitely can't support individualized at the moment.
So here's a question for you. Where's the haptics?
Yes. So haptics. So that was originally intended as, I was hoping to get that in there as one of the main features, because I'm interested in the full immersion. But at the same time, further and further, we went into, this is basically just a big user human-centered design process. The further and further that just kind of started dropping off a little bit. So the most important thing right now is, of course, to get the spatial audio and the spatial audio and visual into effect. And so right now, we're trying to get that up and working first. So the second step, so actually, if you read near the end of the paper, I talk a little bit about user engagement and presence. So right now, we have an issue in the industry in terms of there's not really great regulations out there that encourage people, or I should say require people to do these better spatial designs. So we need to find a different way to motivate people. So I suspect very highly that once we get some haptics in there, so right now it's just limited to user interface, but if we can get some haptics in there later on to say, well, people enjoy it more because I can have better feedback from everything, from a little bit of haptics around the world, like a little bit of some wind, for example, would be nice, but that would increase immersion. And the belief there is that would also increase presence and user engagement. So people, of course, use it more. And if the companies or the government is saying you have to use this, if people start using the software more in general, they'll use it for longer periods of time. So therefore, they're going to start engaging more with the actual design process longer. And ultimately, we think that's going to be good in the long run. But that's going to be, at this point, phase 2.
All right. Thank you very much. There's a lot of work yet to be done there, obviously. Yes. So I think we need to move on to the next talk, the third one, which is entitled Shaping Urban Soundscapes Through Sound Art. And I'm welcoming Catherine Guastavino here. And so Vincent, if you could please start the video.
Hello, and welcome to our presentation on sound art in public spaces. I'm Catherine Guastavino, presenting on behalf of my colleagues from McGill University, as well as our collaborator Simone from Audiotopie, a sound artist collective based in Montreal. I will report the main findings of a field study involving the design and evaluation of a sound installation in a public square exposed to construction noise. The public square Fleur de Macadam is located on Mont-Royal Avenue, a busy commercial street in a vibrant neighborhood in downtown Montreal, with 2 smaller streets on each side and residences in the back. The blue rectangles show the 8 speakers that were used to present the audio material, and they were located all around the sitting area in the center of the square. We deployed the sound installation and collected questionnaires when the installation was on and when it was off, to investigate its effect. But at some point, major road construction work started with associated construction noise that was clearly audible during working hours. So we thought that this would be a unique opportunity to explore the potential of sound art to improve soundscapes in the presence of unwanted sounds, such as construction noise. So Simone D'Ambrosio from Audiotopie created an acousmatic composition for the sound installation by positioning synthetic sounds and moving them through the space. What you see here are 8 different tracks corresponding to each of the 8 speakers that were controlled independently. And this strategy resulted in complex rhythmic patterns in space and trajectories across multiple speakers, giving users opportunity for playful explorations of the space through sound. We will now listen to a brief audio clip. And this is what the space looked like. You can see the speakers. They are the white cylinders that you see attached to the poles. So our research team administered questionnaires to passersby in July and August 2019. We approached the respondents after they'd spent a few minutes in the park, and they filled out a brief questionnaire where they were asked to evaluate the soundscape using semantic scales. Some of them referred specifically to sonic attributes, and others to restorativeness, which measures the potential to take a break and recharge your batteries in that space. We also added questions on the appropriateness for the activities envisaged in that space and perceived loudness. So we collected over 350 questionnaires from respondents aged 18 to 78, and we compared the responses collected in the presence and in the absence of the sound installation to investigate its effect on soundscape evaluations. About 1/3 of the questionnaires were collected during construction hours, that is between 7 a.m. and 3 p.m. on weekdays. So we ran statistical tests on the overall data set and also specifically on data collected during construction hours. What you see here are the overall results. So collapsing overall questionnaires, we see an effect of the sound installation on the ratings of calmness. You see the ratings collected, the min ratings for data collected when the sound installation was off in gray and when it was on in blue. And so in the presence of the sound installation, users rated the soundscape as calmer, even though we were adding additional sounds. But the most interesting results are actually when we look specifically at data collected during construction hours, because there we see a significant effect of the sound installation on many scales, related to soundscape attributes, but also to restorativeness and loudness. So in the presence of the sound installation, the soundscape was perceived as being more pleasant, calmer, more coherent, less chaotic. It also lends itself more to being away or taking a break in that space and conducting activities. And it's also perceived as being less loud, probably because your attention is drawn to the music and not to the construction noise in the background. So the results show that the presence of the sound installation can significantly improve the soundscape of a public square, particularly when it is exposed to undesirable sounds like construction. So these results demonstrate the potential for alternatives to expensive noise mitigation solutions, such as noise barriers or sound masking, particularly in the context of small urban parks in densely populated neighborhoods, when the sound sources might be temporary and not too loud. We also believe that sound art in public spaces can be used to animate the public space and also provides a forum for cultural exchanges and to promote new music. This research was conducted as part of the Sounds in City Research Partnership, and if you're interested in learning more about this, visit our website. Here are a few references cited in the presentation. I thank you for your attention and we'll be happy to take questions.
All right, thank you. Catherine, are you there?
Yep.
Okay, there's a question here on Slido. Construction hours is work hours. Is there a risk this will influence your results? For instance, people might be more stressed during work hours.
Okay, so we did look at the effect of work days or work hours and compared it to weekends in previous years or outside of the construction period. And yes, there are differences, but I would say construction starts much earlier than the space starts being used more like later in the morning and in the afternoon and well into the evening and even into the night. So it's not really a perfect overlap between working hours and the time that the space is used. So we did observe differences between weekdays, for example, and weekends, between evenings and between the rest of the day. And this was actually taken into account for the design of the sound installation. So the content was not fixed. It varied across different periods of the time of the day to reflect times where the space is quieter or less used and to be more active or more busy when the space is crowded. So we looked at that separately. Yes. Does that answer your question?
I hope so. There's no question Slido right now, but I do have a question myself. So the sound was pre-programmed, is my understanding. Is there a possibility, or are you thinking about in this particular setup to have more of an interactive element, maybe in response to how many people there are or what they are doing?
Yes, absolutely. So that is certainly the next step. So what we did in this one, as you said, is that we analyzed the park use from the previous year and used that to identify times of the day where it was more busy than others. But the next step would be to have a fully interactive installation that could also adapt to weather conditions, crowd density. And so we're working on that with the sound designers from Audutopie. That would be the next logical step. We were hoping to do some of that over the summer. It hasn't been possible because we were not able to collect data, but we're hoping to do that next year.
Yes, thank you.
And that is what Valérian will be working on as part of his PhD, designing fully interactive and adaptive sound installations in public spaces.
I think I have time for one quick more question. So the work is very audio and sound oriented. It's a little bit the same question, almost like I asked Richard here. But actually in a different direction. Do you see ways in which the results of this particular study, of these kind of studies, actually can inform the audio design? So maybe feed it back to how you could maybe change the audio soundscape itself.
The design of the sound material presented, or the design of the soundscape of the public space?
Yeah, just wondering if there could be like an iteration with okay, so this particular implementation of the soundscape had all these positive effects, but
Okay.
can you then take that further to designing, even optimize the sound design, so to say?
Okay. Well, maybe I can say a few words about the design process, actually, because we did work closely with the designers and the composer to actually go back and forth between the lab and their studio. So we were using, for example, recordings of that space and then reproducing them into the lab and positioning virtual speakers so that we could determine what the best location would be for the speakers to create the trajectories. So there was a lot of pre-planning and piloting in the Kermit labs before we actually deployed it into that space. And the design was also informed by the analysis of activities conducted in the space. So there was a lot of back and forth between scientific inquiries, if you like, of how the space is used, where the speakers could be positioned so that the sounds would be clearly audible, so that you could perceive trajectories. And I thought that was very stimulating and interesting to this back and forth between the musical practice, if you like, and the kind of results we could get from our research and surveys conducted on that space. To go back to haptics, again, with Audiotopie is also working with interactive pieces of furniture, for example, that you can sit on or that you can use to generate sounds. So that would also be something we would want to explore in a next step. We were limited in terms of what we could do because this was just a prototype. This is a brand new public square, and so it hasn't actually been turned into a permanent design. We explored with temporary designs that were installed for a month each or for a full summer, but the space will be turned into a permanent public square, and that will give us more opportunity to explore haptic design as well.
Okay, I think we're out of time, but I will squeeze in one very fast question. How fast was the construction work happening? So how far was it from the square?
It was about a block away, so it wasn't directly on the square. I don't think that this would have worked that well if it was right next to the square. It was about a block away on Saint-André.
Okay, well, thank you to all the presenters in my sessions. I'm handing over the reign to Christian for the final session. Thank you.
So hi again, I'm Christian Frisson. I'm a postdoctoral researcher at McGill University at the Input Devices and Music Interaction Lab. So I'll be chairing the last session and with 3 contributions, 1 paper, 2 demos, and their common ground, what they share is that they feature interactive multimodal systems fully or partially covering the whole design space of haptic and audio interaction design. So the first is from Gijs Verhoeven and Vincent Lévesque, design of haptic language for gestural control of smart lights. The second will be a demo by Rodolphe Couelly and Vincent Cusson, organic versus synthetic, the polymers battle. And the second demo will be by Felipe Verduro, Suzuka Kokubu, Chonti Wang, and Marcelo Wanderli, called MAP EMG, supporting musical expression with vibrotactile feedback by capturing gestural features through electromyography. So before we start, I would like to remind you that you can ask and prepare questions on Slido. The easiest way for you to find the link is to check the description of this YouTube live stream, or to type the event code 62272. So I'm now gonna give the hand to Gijs, who is going to do a live presentation.
Hello. Good morning, good afternoon, everyone. Today I'm going to talk about the design of a haptic language for gesture control of smart lights. Introduction. So ubiquitous technologies emerge all around us, and often we see that we interact with these technologies with screens. However, we think that screens are no longer the best way to interact with these ubiquitous technologies, because screens take up all your attention, and we would like that the interaction happens more seamlessly within the environment, within the everyday life, using haptics. Our approach is rapid prototyping and user-centered design. And in our result, we have a final prototype in virtual reality, and we made a haptics language. And we chose for the very specific context of smart lighting, because this is well known. There is a user market for this. And there are many interesting interactions possible with smart lighting and gestures. So in our design process, next to mind maps and scenarios of use, we quickly made a lo-fi Wizard of Oz prototype. In this prototype, we could turn on the lights and play haptics as we wanted. And in this way, we could basically try out several configurations, several fundamental design choices early on in the process, without having to spend a lot of time on getting a final prototype. So we could get early insights quickly with this prototype. You see an image of this in the lower left of this prototype. Then our final prototype we made in virtual reality. This is a living room with 4 light bulbs in it. These light bulbs have several parameters, such as the light intensity, the light temperature, and the light color. These bulbs could be controlled with gestures, such as pointing at the bulbs or swiping. And haptics was used to communicate all sorts of messages to this during the interaction, to guide the user, to steer the user in several ways that I will explain soon. I will show a short video of the interaction, of several basic interactions, and the sounds that you hear, those are the haptics. So here you see how the user is, one back. Here you see how the user is scanning in order to see if bulbs are interactive or not, if they're small. Here you see how you can, with the gesture, turn on and off the light. And here you see how delay is communicated. So what happens is that the user does a gesture, and then during the delay, the haptics play to communicate the fact that there is a delay between the gesture and the effect in the bulb. So the components that we used are the Unity software, and we made use of Oculus Rift and the touch controllers. And to get the haptics, we made use of the low-felt bracelet. We choose for a final prototype in virtual reality because this allows for rapid prototyping and for easy explorations of this concept without having to spend a lot of time on technical difficulties with hardware and having to buy all sorts of stuff, all sorts of devices. So this is an overview of the complete interaction that is possible with our prototype. Every number stands for a sort of message that is communicated via haptics. There are a lot of different ones. And in this image, you begin in the middle by pointing at the bulb to select it. And for example, if you then swipe to the right, you go into the ambience mode, with which you can set the parameters of the light, so its intensity, its color. And then, for example, what we used is the number 8 is the boundary. So if you reach the maximum value of, for example, the intensity, then you get a haptic feedback, a bouncy haptic feedback that to indicate that you actually reached this maximum value. And like this, there are all sorts of haptics in the interaction to steer the user. In this slide, you can see on this image below all the haptic signals that we developed in a visual way. On the x-axis of each block, it's the time. And on the y-axis, you see the frequency. And each black dot represents a haptic tick, a haptic signal. And so, for example, here you see all the different parameters that we changed in the haptic signals. And for example, what we did is the repetition. So as you see at 2, the interaction possible, is here what we did is that we linked the number of ticks that you feel when you scan a bulb, when you point at it. The number of parameters is linked to a number of ticks. So if you are pointing at a bulb that can only change the intensity, then you only feel 1 tick when you point at it. And if there's also color, then you get, for example, 3 ticks. Another example is that we used, for example, the frequency, an upwards frequency, for example, at number 1, the gesture confirmation. There's an upwards frequency for positive, progressive gestures, such as entering the ambience mode. And then there is a downwards frequency for more negative or ending gestures. So in our discussion of future work, of course, there is a difference between the prototype in VR on the one hand and the real use in real life. Of course, we have controllers, the touch controllers that mediate the interaction. In normal life, there wouldn't be no such thing. Then in real life, we expect that there would be much more delays and errors. And we did introduce artificial delays and errors. And we found out that especially these complex cases where things tend to go wrong, so there is a delay or something, these are here haptics can shine basically, because haptics prove very useful in these cases to actually communicate that there is a delay, for example. In our prototype, you were always alone. In real life, there can be multiple people in the room. And then, but it's important to note that we found that this virtual reality is really useful for rapid prototyping and a focus on the interaction instead of technical difficulties. We found that haptics should be used sparsely because it can become chaotic very quickly, and the user feels like he loses control, that he doesn't know anymore which haptic signal is related to which gesture, for example. We would like to do a formal user test, and we would like to explore interactions with different devices, such as smart speakers. And finally, we would like to conclude with that rapid prototyping and user-centered design is a good way to find interactions, and for each interaction, what information is needed at what moment. So it is a very stepwise and practical procedure approach. And then the haptics are promising to communicate seamlessly with smart devices in everyday life. However, it's important to use haptic sparsely because it can get annoying or out of control. And then VR is efficient, but it also introduces several limitations and differences. Thank you.
Thank you, Rais, for your presentation. I particularly like that you presented diverse techniques for interaction design, haptics user experience design, which is the name of the lab where you conducted your work, with sketching on whiteboards, etc. So we already have 2 questions on Slido. Is the design of the gestures grounded in some kind of theoretical model, or are they more arbitrary?
They are not arbitrary, but they are not really based on literature neither. They are mostly intuitive. We did very well. We started, for example, with this lo-fi prototype, and then we did several versions of hi-fi prototypes or final prototypes, and we developed several gestures that we felt right or also feasible, and then we implemented those. But it's true that we should verify this either with literature or with user studies, user tests.
And personal add-on to the question, I saw that you, in your paper, you mentioned that some were metaphoric, right?
Yeah.
The second question on Slido. In some bulb setup, the Philips Hue, the mesh network would remove all delay issues, as you would probably have a line of sight with the bulb, but location seems hard. So it's mostly a comment. Do you have any feedback on this comment? You want me to repeat it, maybe?
Yeah, I'm reading it myself.
Okay.
I don't know what the question exactly is. It is true that in our prototype, you always have a line of sight. That's true. While currently with the smartphone, you would be able to activate bulbs that you are not seeing. And in our prototype, you have to see the bulb at the moment.
Okay, was more of a comment. So I will ask another question. So in your paper on the discussion section, you mentioned that copying a bulb's parameter using a grabbing gesture, for example, seemed intuitive, but could not be implemented quickly with the selected hardware and software platform. So my question is, could you tell us more about the challenges in implementation?
Yeah, so we made use of a specific gesture recognition Unity asset, this MyVR asset. And we found that there are some basic gestures in this asset that are easy to use, and you could also add your own gestures. However, these were sometimes hard to recognize, and they were based on they're especially hard to recognize, especially in the Z direction. So if you want to do this, then it often saw it for an upwards or a downwards. And we found out that if the system misrecognizes a gesture, then this is very confusing, because then it turns into some mode, or it does something that you don't expect, because you expect that the system recognizes your gesture, but it doesn't. So this was very confusing. So we decided to take rather basic gestures in the end. But quite some time was spent trying to get this work, but yeah, it didn't.
Okay, thank you. Thank you very much. We'll go to the next presentation now.
Okay, thank you.
Thank you. So the second presentation is a demo that is pre-recorded. Organic versus synthetic, the polymers battle.
Hi there, we are Rodolphe Thiolly and Vincent Cusson, researchers at Emile McGill University, and this is a short video for our demo paper for HAID 20. Those researches are being continuously fed and gathered in the Papierlogic project website. The original objective of this demo was to introduce the HAID community to paper-based electronics as well as custom-based fabrication of sensors, while comparing two symbolic types of materials of today, organic-based materials versus synthetic materials. These goals have been obviously shortcut by the recent COVID events. However, we hope we will be able to provide you a bit of information that could be reused for your own research. Custom sensors fabrication has been widely explored since the early age of electronics. While standard components are being very easy to access, very cost-effective, they are limited in terms of standard shapes and sizes. Thus, the idea of producing your own sensor made of various kinds of material can enable to explore larger custom design and become sort of an open source hardware facility. We've been considering here two possible ways for producing custom sensors of good quality and cost effective and of any sizes and shapes, using either a conductive plastic called Velostar or a carbon-loaded paper from Papierlogic. We practically explored the fabrication of a classical piano design, either made for finger touch at the size of a regular piano keyboard, or made for the floors at the size of the fruits. When mapping force sensor signal to control audio, visual or haptic feedback, repeatability and time response are the main parameters of interest. Fortunately, both interfaces seem to react quite effectively in terms of repeatability and time response, as much for Velostar than for paper. We will now need more time and a live demo to go further with you. We hope you are interested in this research and can reproduce it for your own research. Thank you for watching, and let's keep in touch.
So thank you. We have online with us Rodolphe to answer questions for you. So what I particularly...
Thank you for watching.
Sorry, experiencing some difficulties. Here we go. So what I particularly like about your work is that your organic sensors are made out of paper and they can be recycled. So we don't have yet questions on Slido. Please feel free to ask. I will ask a question in the meantime. So what equipment is required to fabricate your paper sensors? Is it maker grade or industrial grade?
That's the whole issue. You can find industrial paper, but it's not made for this purpose. so you won't find it easily because nobody will sell it to you for this. So I found them with a multimeter going around workshops, art shops, etc. That's the whole idea of the research, is really focusing on what can we make with specific materials, what can we extract from materials. And that's why I think it's interesting for the HAID community, because the sensor response itself will be in the choice of the materials. If you want a reactive sensor, you can better bet from a stiff material than from a foam that will get your energy when pressing it. So I'm really on this side of the research, and the mapping is just mainly an application or a way to show what you can do with that. So I'm not really in high level in this field. I just know enough to make my sensor work and try to answer the request of people, of developers, who on their side, they don't know about the materials. They would not like to spend time on this because it's cost effective, but it's time consuming when you don't know how to proceed. And to finish with your question, you need specific equipment. And I'm more currently on working in a paper mill, general paper mill for many kind of paper. And so I have access to a facility that gives me these resources.
Okay, thank you. Before the last part of your answer, so there's a question that was related that just came on Slido. So do you provide off-the-shelf solutions that researchers can buy to start working with your paper sensors?
That's it. The force sensor I could develop are very, very great. I spent my whole thesis on that, and I really showed you can, with some time and experience, do as good as industrial equivalent, with the advantage of customizing the shape and the size. You can wrap the sensor around the tube if you want. You can. That's really also what can maybe bring something new to the community, trying out things on the hardware side that was not tested yet. And the second objective is to really go further with other components, because the idea is that everything you can put in a paper, you can recycle it very easily with low energy. So you can put gold pigments in the paper and get them back if you want to.
Okay, thank you. So that
not
opens
the case for plastic.
New perspectives for sustainable interaction design, potentially with haptics. So thank you, Rodolphe, for your answers.
This opportunity.
And we're gonna now switch to the last demo presentation and last presentation of this virtual conference, Map EMG.
Hi, my name is Felipe Verdugo, pianist and postdoctoral researcher at the Input Devices and Music Interaction Laboratory and at the Expression team. This video presents the Map EMG, which is a work-in-progress setup that produces a vibrotactile feedback based on pianist muscle activity captured through electromyography. Gestures are an essential element of musical performance. They allow musicians not only to effectively produce sound from the instrument, but also to embody the expressive content of the musical discourse. The objective of the Map EMG is to make perceptible through vibrations a rather non-visual aspect of pianist gestures. Activations of trunk muscles related not to motion of body segments, but to the embodiment of musical tension, which is a central feature of Western tonal music. Our ongoing work is based on the data collected during a pilot case study where I performed several excerpts from Beethoven late piano sonatas. Muscle activations at the abdominal and pelvic floor regions were captured with 10 surface EMG electrodes, and musical tension levels were subsequently recorded with a linear slider. To generate the vibrations, we used the VibroPixels, a wearable vibrotactile device developed at ITMIL, equipped with ERM motors and controlled with an interactive software programmed in Max. Processing of EMG data was based on standard methods, and to control the vibration amplitude of VibroPixels, we scaled mean values of EMG data every 300 milliseconds. We first used mean data of external oblique muscles because on one hand rectus abdominis muscles showed rather small activations, and on the other hand pelvic floor muscles are located further from the skin surface. However, recent experience with vibropixels showed actually better vibration outcomes related to musical tension when using mean data of both external oblique and pelvic floor muscles. This latter method is presented in the following demo, where the LEDs integrated in the vibropixels provide a visual reference of the vibration amplitude. Future work on the MapEMG will include perception tests and adaptation of the setup to live musical performance and pedagogical contexts. Thank you for your attention.
Thank you, Felipe. So Felipe is here with us to answer questions. So please feel free to ask questions on Slido. So in the meantime, I would ask one. So Felipe, could you give more details about how vibropixels helped you to figure out that mean data of oblique muscles and pelvic floor muscles instead of mean data of just oblique muscles that was better input to control the vibrotactile feedback?
Yes, actually, so as explained in the, can you hear me well?
Yes.
Yes, good. So as explained in the demo paper, we first use data of external oblique muscles because they actually seem kind of visually correlated with the musical tension data that we collected. That was the musical tension was the performer's idea of musical tension, right? For the different experts we recorded. And so pelvic floor muscles are kind of farther from the skin surface, so the data is less reliable in a way, so there's more noise because placement is more difficult because there are not surface muscles. And as also like the rectus abdominis muscle was, the activations were really like low, right? So when using vibropixels, this seems very like a very good approach. Like the vibration seemed related to the musical tension levels without listening at the same time to the audio file of the different like piano excerpts, right? So when we integrated at the same time the audio and the vibrations, the result was good, but could have been a little bit better because the peaks were there actually for the tension levels, but they didn't last enough in relation to what we were listening, right? So pelvic floor muscles had larger peaks, and that didn't seem like a big plus just looking at the data, because with the mapping we can control like the amplitude, right? So but what was very different when we integrated the data from pelvic floor muscles is that the biggest weren't just like higher, but always longer. So it was the length of the tension peaks, so the muscle activity peaks, that produced actually a better vibration outcome, because it was like more related with the musical stimuli in real time, right?
Okay, thank you. So I will ask a second question, sorry. So do you have plans to use MapEMG in remote musical performances in real time, for instance, and generating vibrotactile feedback maybe with smartphones if vibropixels are not part of the everyday devices that the audience can have?
Mm-hmm. Yes, actually. Well, so for remote performance, I think that would be a good element to add to like to musical performance that is transmitted virtually, like on the internet. and the use of the smartphone is something that has that we like. It has been in some discussions. It hasn't been implemented yet, but I think it would be a very good idea to make it possible, like to, how do you say it in English? So more people can have this feedback.
Democratize.
Right? Exactly. So either like on like a non-presential performance, or in a actual concert, right? Because at least nowadays everyone has a cell phone, and to have, I don't know, 200, 300 micropixels is kind of a challenge, right? So that would be actually a good thing to develop.
So it will be one of the first times we won't be asked to turn off our smartphones before the performance.
Exactly. Right.
All right. Thank you for your answers and your presentation.
Thank you. Thank you for the organization.
So we are at the end of session 3 and end of the conference. So we would like to thank all authors, reviewers, and members of the organizing committee for this first virtual HAID. And we hope that HAID is going to be organized again next year, possibly virtually. So we invite you to continue this discussion over the HAID Google group. You can find the link on the HAID website of this year. So thanks again also for your remote participation.